Okay, so the topic for this week is extrasolar planets. Now, this is an immensely fascinating field because this is something that we literally could not have talked about in an astronomy class even 5 years ago. This is the single most active field of research in all of astronomy right now, and I also think it's the most fascinating just from a pure humanistic standpoint. So, again, the idea of an exoplanet, the idea of an extrasolar planet, is a planet which goes around some other star other than our sun. We know there's 100 billion stars in our Milky Way. We know there are 100 billion other galaxies out there. But until very recently, within the last decade or two, we've literally had no idea whether there are any planets out there whatsoever, and even less idea if they are, what they would be like. And the really cool thing is that just within the last 5 or 10 years, we've begun to actually be able to answer these. And the data that we have coming in every month now, within the last year and a half, has been just phenomenal. So there have been huge advances in this, even within the last few months. So the reason I want to post this video is because even since your textbook came out, which was this year, and since I think the date of the last writing before they published it, which was probably the end of 2012 from what I can see, there have been even significant advances here. So your textbook is literally out of date after being only 6 months old. So I'm just going to go through some current websites, which you guys can all see on your screen too, and just kind of point out what the state of the knowledge is as of right now, as of, was it October 2013? And this is likely going to change even before the semester's over. So this is how active this research field is right now. So the first thing is, yes, we began discovering these other planets outside of our solar system. Yes, they exist, which is fascinating in itself. Now, there's a number of ways of detecting them. Your textbook goes through a couple ways. One way is looking for stars. As the planet goes around it, the star is kind of gravitationally pulled towards that planet. And every time the planet goes to one side, the star gets a tug in one direction, and then when the planet goes to the other side, the star gets a tug in that direction. So we see this back and forth, essentially a wobble of a star, due to the planet's gravitational influence. Now that's called the astrometric technique. Now there's another method we can use if we can't actually see the star wobble left and right, but if we can see it move slightly back and forth. So if there's a planet going around it, and what we look for is a back and forth motion. And it's a little bit more complicated, but in essence what we're seeing is the Doppler shift. It's the same thing as when a police car goes past you, you hear the siren go from a high pitch to a low pitch as it moves past you. What's happening is the wavelengths are being shortened as the car approaches you, and they're being lengthened as the car passes you. And so when we're dealing with sound, this sounds kind of like a noise. And when we're dealing with stars, what actually happens is, obviously they're not getting enough sound that we can hear. But what is happening is the light from that star, when the star is getting pulled towards us, by that planet, the light waves get shortened a little bit. We see that as slightly bluer light than average. And now when the star is moving away from us, we see that as slightly longer light, or what we call redder light. That's how our eyes detect it. So there's that Doppler shift, where it's moving towards and away. And I mean, actually, it's making a circle, but we can't see the left and right part of the motion. All we can see is the front and back motion if we're using this technique. And so that's another way that we've been using technology to find these planets, or at least evidence that there's planets going around these stars. Now, the third method is the most important for our discoveries today, and that's called the transit method. What's happening here is, imagine a star, well, I'll show it like this, a circle, giving off light, and imagine there's another small planet orbiting it. Now, every time, if we happen to be directly on the line of sight of the plane of that solar system, of that star system, every time that little planet passes right in front of the star, from our point of view, it blocks out a little bit of that star's light. So it looks like the star gets slightly dimmer, and then goes back to normal, and then maybe 3 months later, it gets a little bit dimmer again, and it goes back to normal. And then 3 months later it gets a little dimmer again, and it goes back to normal. If we see this periodic shift of the star's brightness, we're not seeing it move left or right, we're not seeing it move front or back. All we're seeing is the star get a little bit dimmer on a regular basis. And if we're seeing that, then what happens, what we know is that there's a planet that's eclipsing that star. We call it a transit. The planet's passing in front of that star with respect to us. And the really great thing about this method is that because we're not looking at the gravity of the planet tugging on that star, and because we can see even very slight changes in that star's brightness, we can actually detect very small planets, even smaller than the Earth. And so this isn't limited by how strong the gravitational force is between those two things. It's not limited by actually having the star close enough to see it move left and right, for example. The only thing that limits this is simply just, if we had a very, very tiny planet, we might not be able to see enough of a shift of the star's brightness. But this is the most important method today because this is in fact the method that the Kepler mission is using, which is arguably the most successful mission in the history of NASA, and for reasons that you'll see here. So I want to go through what we have learned from the Kepler mission in particular, and from all other missions combined, which turns out today we can focus on just what Kepler is looking at and still get amazing results. So to date, our textbook has quoted the number of discovered planets, and again this was 6-8 months ago, as a few hundred, which that in itself is pretty amazing, that we found a few hundred of these planets outside of our solar system. But what Kepler has announced is just absolutely stunning, that if we take all of the candidates for planets that we think we've discovered by Kepler, Kepler has discovered to date almost 3,500 planets. Now, the reason it says unconfirmed is simply just that we need some follow-up observations to make sure, if it goes every 3 months, we need a few cycles of that. Or maybe every 3 years, we need, 6 or 9 years to be able to confirm that it actually is a planet. But to the best of our guesses, Kepler has discovered over 3,000 planets, which is amazing. And if we add up everything that Kepler discovered, the confirmed, the unconfirmed, all the other methods, we have over 4,000 planets that we know are out there outside of our solar system. And I think that's amazing. And this is, again, something that's literally every day we're adding to this list. Every year we're growing by hundreds and hundreds of planets that we're discovering. If you look back even 6 years ago, the number is at 1. And since then it has literally skyrocketed. So this is the most active field of astronomy research. And it's just fascinating to see that, yes, there are other planets out there. And now the question becomes, how similar to the Earth are these planets? Are they capable of holding life? Or are they all just Jupiter-like, too far or too close to their sun? So that's an answer that we didn't have when this hunt started. But as more and more time has gone on, we've actually been able to see more and more what these other planets are like. So there was a really cool comic, a graph posted. This was in June 2012. Some of you guys might be familiar with the website XKCD. It's kind of a nerdy online comic strip. But as of June 2012, and again there were only 700, known planets out there. This is what the graph of all the planets look like. Now each circle denotes the planet's size. So what I think is amazing, if you see right here, this little box of dots, you can only really see 4 of them, or maybe 6 if you look really strongly. But this is all the planets that we know about in our solar system, the 8 planets, not including Pluto, in our own solar system. But if we look at all of the other planets out here, the vast majority of them, as of June 2012, looked Jupiter size, about that size, or significantly bigger. There were only a very, very few number of these small planets, and many of them were only about Neptune size, relatively small, but not quite as small as any of the terrestrials discovered up to that date. And in fact, this is actually kind of what we'd expected at this point. Before the data from Kepler came rushing in, there was what's called a systematic bias towards finding the largest planets. And the reason for that is when we use the astrometric technique, watching gravity pull that star, or the Doppler shift technique, watching, again, gravity push and pull that star towards and away from us, we're biased towards seeing only the largest, the most massive planets. And also we're biased towards seeing planets that are closer to their sun, because we know that planets closer to their sun have a stronger gravitational influence. So again, it did look like even just a year ago that most of the planets out there were Jupiter-like, very massive, and many of them were, strangely enough, very close to their star, even closer than Mercury, or 10 times closer to their star than Mercury is to our sun. But this has all changed. So even in the last year, now that the data from Kepler has really gotten time to kind of take off, if we were to make this graph today, you'd have to make it 5 times bigger than the size of my screen right now, and you'd also have to make many, many more small dots. And the reason for that is, this is an announcement from January 7th, 2013, which just happened to be at the annual American Astronomical Society meeting, which is the biggest meeting of astronomers in the world every year. I happened to be there, which was awesome because I actually saw this talk given at the time. But so the big announcement there was that Kepler announced 461 new planet candidates. Essentially 461 new planets that are almost certainly planets, but we need to make further observations to confirm them. But not only that, the even bigger result, that literally the whole meeting was abuzz about this. This was the main featured talk of the whole conference. The most important thing is that the findings show a steady increase in the number of smaller sized planets and the number of stars with more than one planet. So this is important because, go back a couple years ago, again, the most planets we were seeing were big Jupiter-like planets. But as Kepler's had more and more time to process the data, we're seeing that, in fact, there are many smaller planets out there, much more like Earth, or much more maybe what we call super-Earths. So I want to go to the graph right here, zoom in on that a little bit. And so this shows, as of, again, the beginning of this year, which has even changed since then, looking at categorizing the planets by how large they are, according to the planet's radius. So what Kepler is seeing is what we think used to be the dominant type of planets based on data from a few years back, very large, much bigger than Jupiter, or Jupiter-sized, is in fact not necessarily the norm. We're more likely to see planets that are around the size of Neptune here. The majority of the planets we've discovered now by Kepler have been roughly Neptune-sized, or a little bit larger than Neptune. So, still probably mostly made of gas, but definitely getting closer to the size of Earth. But the neat thing was that we're seeing many, many more planets that are what we call super-Earth size, up to about twice as big as Earth. And actually, this was the most important announcement because we're actually now seeing on the scale of hundreds of planets, 350 planets, that are less than 25% larger than Earth. So Earth size, 10%, 20% larger. A couple of them are even less than Earth size. And we're actually beginning to see that these things exist out there. And we know where they are in the sky. We know what their properties are roughly. We need obviously more observations to see exactly what they're made of and so on. But the thing is, so even though we have planets that are like Earth, not all of these planets are necessarily going to have life. And this is, again, the holy grail, finding a planet that has properties capable of there being life on it. So here was, again, this is another consequence of the meeting. So the question was, how likely are we to have Earth-like planets, regardless of where they are, how close they are, how far they are from their star? But this is another result of the conference. We think, probabilistically speaking, according to simply the law of probability, what we're seeing now indicates that at least 1 in 6 stars has an Earth-sized planet, within about 20% or so of Earth's radius. 1 in 6 stars has a planet like Earth. Again, it may not be at the right distance from its star to have life, but at least Earth-like planets are actually very common. And I think this is fascinating here. If you look at just this statement, since the Milky Way has about 100 billion stars, according to the data, the probability, there are at least 17 billion Earth-sized planets out there. And I think that just blows my mind. And the fact that we can even make any sort of statements about this, backed up by any sort of data, let alone very strong data, is amazing. So let's look at some more things that have come up in the last few months even. So this was in February of this year. There was a big announcement that Kepler has seen a planet that's even smaller than Earth, significantly smaller than Earth. So Kepler 37c, it's just the planets. Well, I'll avoid the naming, but if we look at this in size, there's Earth, there's Mars. Here's a planet that's even smaller than Earth, which is pretty cool. But not only that, this planet actually has a partner planet in the same star system as it that's even smaller than our moon, Kepler 37b. It's smaller than Mercury and only slightly larger than the moon, I should be correct. So, going by this. But the point is, we're seeing planets that are literally as small as moons now. And this is really great news because in the past, if we thought that all the planets were gas giants, likelihood for life on any of them is probably very low. But if we're seeing Earth-sized, Mars-sized, even moon-sized planets, that's amazing. And again, these two planets are actually in the same star system, and we're seeing many of these stars that have multiple planets that are all going around, just like all the planets in our own solar system. So now the question becomes, now that we know there are planets out there that are similar to our terrestrial planets, and we know there are small enough planets out there that very possibly have the same constituency, the same properties as Earth, how many of these planets are actually close enough to their star to be warm, but not so close to be overheated? So we call this the habitable zone. Just close enough for there to be liquid water, but not so close that everything burns up. It's kind of like the Goldilocks zone. Not too hot, not too cold. So again, we call this the habitable zone. And the question is, are any of these Earth-like planets in the habitable zone? This is the holy grail of finding a planet in the habitable zone and then doing further follow-up observations to see, does it actually have life? So here's the big news. we have the habitable zone gallery. By the way, this is a really cool website, hzgallery.org. And this keeps track of all the habitable planets, I'm sorry, all the planets within the habitable zone that we're seeing. And right now, the count of these planets within that zone that's not too hot, not too cold, is at 44. And the question mark just indicates not all of these have follow-up observations that have confirmed for sure that that's where they are. But right now, the planets with the orbit that we know is in that habitable zone is at 44. And this is even from when I posted the slides from when I did this last semester. This was only at 16 or so. So we're finding dozens and dozens every year at this point now. So how many of these planets in the habitable zone are Earth-like? Because not all these habitable planets are small, the size of Earth. Many of them are actually Jupiter-sized. So how many Earth-like planets are in the habitable zone? That's really the million-dollar question here. And the cool thing is, this came out a couple years ago. It needed some follow-up observations, but one of Kepler's first findings was a planet about twice the size of Earth, so relatively Earth-like, maybe super-Earth, in its habitable zone. And the logical follow-up here is that if it's in the habitable zone, it could have liquid water on it. If it has liquid water on it, we know that's where the first life on Earth developed. So we might actually be looking at the first planet we've ever discovered that we think life does indeed exist on it. Obviously, we can't confirm this. Sorry, there's an ad playing. Obviously, we can't confirm this at this point, but we have evidence of there being planets in their habitable zone similar to Earth, which is amazing. Now, the cool thing about this is we can actually plot up what the solar system looks like around it. And so here, this is our own solar system. The green region is the habitable zone, and we see Earth's orbit, the blue line around here, is a little bit close on the inside of that zone, but also Mars and Venus, you could make the statement that they're very close to the habitable zone. They just happen, their greenhouse effects aren't quite suitable for having life. But then here's this planet, and this star is habitable zone, and we see that that's actually a pretty similar orbit to what Earth's is here. So really cool stuff here. And now, so again, this was actually as of a year and a half ago or so, and even since this, we've discovered more and more of these things. So one of the other big announcements at this AAS conference that I was at was that NASA actually found 4 of these planets, 4 of the 461 that discovered. 4 of those planets were Earth-like in the habitable zone. And this was just an absolute first. The fact that we're finding numerous planets that are Earth-like planets, liquid water probably exists, and the logical jump here is there life out there? And so I just think it's difficult to underscore how amazing the research that is going on right now actually is, and how fast we're advancing our knowledge of this, and getting so close to possibly being able to answer and make the announcement, there's life out there. Now, the one big loop that we have to get past, or the one big hurdle we have to get past right now is, we know the planet's sizes, we know many of their masses, we know how close to their star they are, but we can't say anything about what the planets are made of or what the atmospheres contain. And so the smoking gun here is going to be looking for atmospheres that have similar compositions to our atmosphere. And the only reason, by the way, the only reason we have oxygen in our atmosphere is because life developed a few billion years ago, and over time, photosynthesis, which is unique to life, has slowly changed our atmosphere from carbon dioxide dominated, like Venus and Mars, to they've converted that CO2 into oxygen over time, so that now the oxygen in our atmosphere, and in fact the ozone layer, which is also made of oxygen atoms, is a direct result of there being life on our Earth. And so what we need to do at this point is to take what's called spectroscopic measurements, looking at the spectra from these planets and seeing what the atmospheres are made of. And unfortunately, we don't quite have that technology yet, but the technology should be there in the next about 5-6 years or so to actually be able to look into the star's light and be able to separate the light from the planet from all the light coming from that star. And so again, this is going to be the next huge step that we make, being able to actually document what the atmospheres in these planets look like. And maybe I'm being a bit overly optimistic here, but I'm going to go out on a limb here and say that within our lifetimes, we are going to be the first civilization, or the first generation of civilization to announce and to know with real data that we are not alone here. I strongly believe that within our lifetimes, we're going to be able to witness the announcement that we have discovered another planet with life on it. And I just think this is incredible. So that's why this whole field is so fascinating, and that's why there's so much research going on, because we all want to be able to say that we're not alone. But this is exactly where we're going to be finding that discovery from. So again, some of these planets, it's cool to keep track. Exoplanets.org, the HZ Gallery. So check them out on your own time. But yeah, that's what's going on right now in astronomy. All right, bye.